Hello students, in this lecture we'll proceed from group to subgroup, subgroup of the group. First we'll have an very clear idea of what is subgroup, how it is related to a group, and what is the relation between their binary composition of the non-empty sets. Then we'll discuss the properties of subgroup and so on in this lecture. So let's have a very clear, lucid idea of the what is a group subgroup. We have studied in the previous chapter that these algebraic structures, this set of integers under the binary addition, set of rational number under the binary addition, set of real number under the binary composition of addition, set of complex number under the binary composition of addition, and set of rational number binary composition of multiplication, set of real number under the valuation of multiplication, set of complex number under the valuation of multiplication. They are all groups. This means all the four properties holds under this composition and under the composition multiplication and under the composition of addition of this set of numbers. Right? Now we also know that set of natural number is set of whole number, is set of integer, is set of rational number, is set of real number, is set of complex number. This is the how the different number system are related to each other, how one set is contained in the others, as a proper subset of others. Therefore we can conclude that now this is set of rational number, set of rational number. So set of natural number under addition, if you take two is a group, subgroup of the set of rational number over the binary of addition. Set of rational number, natural numbers. This is subgroup of this. Is the set of natural number set of natural number is this will not be set of natural. This is a set of integer, rather set of integers. This is not a set of rational number, but this is a set of integers. Set of integers. Set of integers. Right. Set of integers. Set of integers is a subgroup of set of rational number combined to addition, and set of rational numbers, set of integers is this under the subgroup of this set of rational number. The addition is a subgroup of the set of real number and so on. Set of natural number is not a subgroup of set of natural numbers. The set of this is not set of integer z. Set of integers. Set of integers is not a set of integers under the binary composition addition is not a subgroup of set of real number, set of rational number over language of multiplication. And set of rational number under binary composition is not a subgroup of the set of real number under binary multiplication. Now from these examples we will conclude, we'll find the definition of subgroup. Therefore we not only require that the set of one group be a subset of the other group, but also that of the group population on the subset be the induced operation that assign the same element, induced operation that assign the same element to the each ordered pair from that subset, and by the group operation on the whole set. Let us understand this in We not only require that the set of one group be a subset of the other group, but also that of the group operation on the subset to be the induced operation, same operation. Induced operation, what operation on the group subset must have same operation. Number one, that assign the same element to each ordered pair from that subset by the group operation on the whole set. Very important. Now I'll make you clear that with an example. Let's take an example. We cannot regard the set of rational number, positive rational numbers under the binomial addition as contained in the set of real number under the binomial addition. The binomial multiplication is addition. Even though set of positive rational number is contained in the set of real numbers, as in this case we have 2 and 3 are two positive rational numbers and by coefficient multiplication, so 2 into 3 is equal to 6. This belongs to, so this belongs to Q, and this 2. Now now 2 and 3 belong to real number and 1 is addition, so plus is 5. So this belongs to R. Now we have taken order pair. This was subset of this. Subset of this, but bind coefficient different. Now when we applied, if we applied the, we take the order pair 2 and 3, 2 and 3 in these two sets, we applied operation, binary operation, we got the different elements. Means what does it imply? Means both the sets, set or subset, they must have the same binary composition. Means the resulted element must be the same. If the resulted element does not come to the same, then we say that one set subset will not form a subgroup of this. The algebraic structure, this set of rational number under the binary multiplication and set of real number under the composition addition are groups. But this is but set of rational number, positive number over composition multiplication is not a subgroup of set of real number. Now it's very clear. If you take an ordered pair, you must get the resultant must be same. Means that implies both the if one is subset of a, they must have the same binary. So now let's define the this had made you the idea of the subgroup very clear. Now let me define the subgroup. Sub sub means subset, group subset of a group, subgroup. Definition is a non-empty subset H of a group G under this binary composition O is said to be a subgroup of G if this H with the same binary composition is itself a group. Right? H is a subset of G, means all the elements of H and G and binary are same. So this algebraic H with the same binary composition must form a group, means must all the four axioms must hold to closure, associative, identity element, and inverse element. They must exist in H, then H subset of G, and all the four operation holds true in G. Therefore, then this will H, then this algebraic structure is called subgroup of this G. So in every case, elements of H are elements of G. G. So while proving the subgroup, we use the concept of group with the same method. Now let's make something clear. Every group G has at least two subgroups. कौन से? Every set is subset of G, and this identity element belongs to every group. It does not belong to every group. So set singleton set with the identity element and the group itself, they are the two subgroups of any group G. These two subgroups are called trivial or improper subgroups. If H is a subgroup of the group G, such that H is neither equal to the singleton set of identity element and the G itself, then H is called a non-trivial or proper subgroup. subgroup. I'm saying subgroup subset, and have if any subset of a group satisfying all the four axioms, that is the subset. Now, for example, we know that the set of real number under the value of addition, the set of all real numbers under the value of addition is a group. Also, set of real rational number under the value of addition, set of value of addition is also a group. And Q is a subset of R. Therefore, this set under one addition is a subgroup of this. Now, now we are making it clear the concept of subgroup with help of examples and definitions. And another example: set of positive rational numbers, binary addition, is a group. This is a set of positive rational number. Is a Q set of positive rational number is subset of set of real number. Also, the set of real number under constant addition is a group. Now, but set of real numbers, positive rational numbers under addition, sorry, multiplication is not a subgroup of set of real number under addition. We have discussed this in this example. Example of this. Now, another note. Let's note. If H is equal to set of rational numbers addition is a subgroup of the G under the binary composition set of real numbers addition, and K is set of integers under the addition is a subgroup of H. H is a subgroup of the G and K is a subgroup of H. Then K is also subgroup. K is also subgroup of G. H is a subgroup of G. K is a subgroup of G. K is a subgroup of H. Then H is also subgroup of G. This example generalized the concept of subgroup. And now another if H set of rational number, set of integers over the addition, K set of rational number over addition are two subgroups of a group G, and H is a subset of K, then H is also a subgroup of K. It is also a subgroup of K. So we use this concept while doing this. Subset, for any subset to be a subgroup, it must be a subset of the set of non-empty set, and the binary composition must be the same. If H is a proper subgroup of G, then it is denoted by H is less than G, H is less than G, H is not. In this way means H is a proper subgroup, means at least one element of H is less than G. Right? Now let's discuss the properties of subgroup. Prove that the identity element of a subgroup is the same as the identity element. We have proved in the property group that identity element group is unique. So let G is a group, H is a group. And we are proving it by contradiction. Let E and E dash be the identity element of G and H. G and H, respectively. E is the element of G, group G, and G with binary composition. What the binary composition is. And H is a and E dash the identity element of the group subgroup G. Now our aim is to prove E is equal to dash. We prove it by contradiction. Let A belongs to H. We take an element from this. Now E dash the identity element of H. Therefore, and H is a subgroup. Therefore, A into E dash is equal to A is equal to E dash into A first. Now also, if A belongs to H is a subset of G. Because H is a subgroup of G, so H must be a subgroup of G. So A also belongs to G. G is a group, and E is the identity element of G. Therefore, A into E is equal to First and second implies A into E is equal to A into E dash is equal to A, and A into E is equal to A. This implies A into dash is equal to A is equal to A into E. We have, let A is equal to E dash is equal to A. Now G is a group. So we have read in the property group that both cancellation law holds true in the group. Apply left cancellation law. We got B dash is equal to implies the identity element of a group and subgroup will always be same. Next is prove that the inverse of any element of a subgroup is the same as the inverse of the element in the element regarded as the element of a group. Inverse element of a element will be same in the group as well as subgroup. So let G is group except G. I'm saying G group means all the four exam true. Subgroup G, H subset of G, but all the four exam also hold true. User associative identity and inverse element exists. Let E is the we proved in the first property that E identity element of group and solution. Let E is the identity element of the group H and A belongs to H. If A belongs to H and H is a subgroup G, so H is subset of G, so A also belongs to G. Now again we have to make the contradiction. Let us suppose that B and C are the inverse element of A in H and G respectively. In H, B is the inverse of A. In G, C is the inverse of A. If B is the inverse of A in G in H, H is a subgroup. Therefore, B into A is equal to E. B is equal to E is equal to A. Similarly, C is the inverse of A in G. Therefore, B into C into B is equal to C into A is equal to E is equal to. Now, from this equation, B into A is equal to E is equal to C into A, or A into B is equal to E is equal to A into C. Now again, this implies either this or this. B A is equal to C A. Now C is common. ABC also belongs to G. G is a group. Right and left cancel true. So apply right cancellation. Now we got B is equal to C. Inverse of hence inverse of any element in a group and subgroup is C. Inverse of element, whether we are finding inverse of element in a group or subgroup, inverse element same. So we have read in the property of group that inverse if inverse of element is, that is unique. The same case is in the subgroup. Prove that the order of any element in a subgroup is the same as the order of the element regarded as the element of a group. So in order of element, whether we discuss find the order in a group or a subgroup, the order of element remain the same. So that is the subgroup of the group G. E is the identity. If you want to find the order of element, E is the identity element of both. We have proved the first property. Now let A belongs to G, A belongs to H, such that order of A is equal to H. When N is a finite least positive integers, such that we can order of A is equal to N. Definition of order of an event, where N is the finite least positive integer, such that is well. Now A belongs to H. H is a subset of G, therefore A also belongs to G. The first and second implies A is for N is equal to E, but also belongs to G, because G is a group, therefore order of E is the same. Thus, order of any element in this group and subgroup is the inverse will also same, and order of element will not change whether we take it in the group or subgroup. Prove that the subgroup of an abelian group is a subgroup of an abelian group is abelian. Commutative property. So out of fourth, we are discussing fifth property also. Let H is a subgroup of a abelian group. Now, prove is H is a abelian. We know H is a subgroup of G, so H is a subset of G first. And if you take two elements belong to H, any two elements out of whatever number of elements H have, we will take any two of them. And if A belongs to H, subset of G, this implies AB also belongs to G, but G is abelian group. Therefore, A into B is going to be into A. Is that group? So, therefore, from this conclusion, we conclude that A belongs to H. This group 2 implies for all A belongs to H. We have to include A, H is also this group, and completed the whole 2 become a group. Now, some conclusion from this. Non-abelian group may have an abelian group. If we have an abelian group, its subset will always be abelian. Now we'll conclude some other result. A non-abelian group may also have an abelian group. If you take the two subsets H and K, H is equal to minus 1, 1, and K is equal to minus 1, 1, minus iota, iota, are the abelian subgroups of we know for the composition, we have to write the composition for this and this, we can conclude this thing. They are both are abelian group. This abelian group and this abelian group of a non-abelian group cuvette quaternion under the number. We have this we have discussed the cuvette. We have discussed this in this set of square root of unity, and this, we have discussed this also for root of unity. They both are abelian group or this is abelian group. Now again, non-abelian group may also have a non-abelian group. In non-abelian group also have abelian group. In non-abelian group may also have a non-abelian group. So this is example what this is. Uh, special special second order second order matrices over set of reals, and general second order matrices over reals. This is a non-abelian group, and this is also non-abelian group. So non-abelian group, this example we will discuss it in the group in different example. We will discuss general nth order. Nth order same holds for the second order. Thank you very much.